So my presentation today is on the determination of tissue optical properties from optical signals. So optical property determination in biomedical optics spans several spatial scales. People are looking, like Giacomelli and Adam Wax's group, they're looking for the single scatter size and shape using Me or T matrix scattering phase functions. So that's down at the cellular level. And then Professor Zhu showed how he's looking at thicker tissue, fingers, trying to determine the optical properties, and he uses Monte Carlo simulations of the radiative transport equation. And then onto thicker tissue, Brian Pogue's group are using diffuse optical tomography. They're using finite element methods, solutions to the RTE, and for thicker tissues, often the standard diffusion approximations are used to solve the RTE. So the models that we are using to determine these properties at the different spatial scales are similarly matched with computational models that are appropriate for that spatial scale. So for this presentation, I'd like to describe what's involved in determining these optical properties. It involves a chi-squared minimization, looking at some model functions, both analytic, deterministic solvers, and stochastic solvers. Some optimization methods. You heard about the lookup table. Also, there's direct search methods, and then gradient-based methods. What advantage do you have when you have gradient information? I'd also like to discuss a stochastic inverse method that involves perturbation and differential Monte Carlo, and then touch on very briefly optical tomography, and then show some examples, little case studies in which we determine optical properties given spatially resolved reflectance and spatial frequency domain reflectance, since space is the theme of today. So you saw this picture from Jerry earlier in which we have this forward problem. We have some optical or physiological parameters that we are interested in, and we have some sort of model. And using that model, we get a measurement prediction. This is the forward model. And this is very well posed. A unique solution exists. But the inverse problem, in which you start with these measurements, you use this model function to produce parameter predictions, as we have discussed, can be ill-posed. And the success of this inverse problem solution is affected by the choice of your model function, the parameters that you're looking for, and the type and quality of the measurements that are involved. So I'll go over the chi-squared minimization. The goal is to fit a model function with these adjustable parameters that you're trying to find to a set of measured data. So say you have M measurements, and I've notated them by y hat. And a model function y that has p adjustable parameters. So these parameters are your optical properties. Maybe they're your mu A, mu S prime, N and G, or they're your chromophore concentrations. And the goal is to find a unique vector A, if it exists, that minimizes this chi-squared function, where here's your measurements, here's your model prediction at these parameter values, and this denominator is the standard deviation of the measurement. If you know that, it creates a weighted chi-squared. It allows you to weight appropriately the different summands within this sum, adjusted per the standard deviation of that measurement. A larger standard deviation will deweight that particular measurement. The formulation of this equation relies on two key assumptions. First, that the measurements are mutually independent, and that the measurements are normally distributed about a mean that is the model function. So if either one of these or both of them are violated, and the use of this equation is used to invert or solve some inverse problems, you may run into problems. So keep that in mind when you think about your choice of measurements, model, and parameters that you're looking for. So let's break this down a bit as far as the different components. The y-hat are your measurements. We want at least as many measurements as unknowns, so we want m, the number of measurements, to be greater than or equal to p, the number of parameters that you're searching for. Are the measurements placed at locations or times where they're sensitive to changes in the parameters that you saw in Professor Zhu's nice plots of where changes to absorption are sensitive? You need that path length information. You need the smaller spatial frequencies as well as, or conversely, the longer source detector separations. Is there redundancy in the measurements? Are there measurements there that aren't adding any benefit or information to determining the optical properties of the parameters that you're looking for? And how are the measurements calibrated? Yesterday you saw how when you were using the integrating sphere that you calibrated the measurements with I think a dark field and total transmittance. And so if that's involved, you have to make sure that you adjust your model function accordingly. Looking at the model function now, is the model function accurate for the measurement domain? We saw earlier that the standard diffusion requires certain assumptions about the optical properties. Mu s prime has to be greater than mu a. And so you want to make sure that your model, if you choose SDA, that you're in a measurement domain that is appropriate for its application. Is the model function sensitive to changes in the parameter A? Again, that's something, for instance, SDA has no knowledge of G, so it would not be able to give you any information about the anisotropy factor. Also, even if the model function involves that parameter, it could be that it's not sensitive to it in the domain that you're looking at. Can the model function provide fairly quick predictions for use in an inverse iterative scheme? Many of the inverse solutions involve an iterative scheme, and you'll need, that's the reason why Monte Carlo sometimes has been precluded from use in an inverse solution in the past. I'll show you in later slides how we've used it. But you want something that you're going to be able to provide this forward model prediction at various parameter values while you're moving through chi-squared space trying to find the minima. Do the model functions need to be integrated to match the measurements taken? So, you have maybe a reflectance at a point, but you have some sort of camera and you have a pixel. Do you need to integrate that reflectance of the model based on that pixel? And do you have an estimate of the measurement error? And like I said before, if you do, it can provide a weighted chi-squared equation for you. So we saw earlier that the SDA has this requirement. So our model function, when we choose the SDA, needs to be applied to homogeneous or layered. There's a SDA layered solution. There's a SDA solution for a sphere, an embedded sphere. But as you decrease spatial scale or you increase absorption, then you're going to need these higher order PN solvers that I think Boston talked about earlier. And if you need what I might call P infinity, then we're going towards a Monte Carlo, where you need complete angular information, very complex tissue definitions, and this would be the comparable model that you would use. Finite element methods can also be applied. And the measurement domains, as you saw from our GUI, we have spatially resolved measurements, spatial frequency measurements, FX, time or temporal frequency, wavelengths, or any combination of the above. And the parameters that we are interested in are the optical properties, possibly chromophore concentrations, or scatter size. And of course, the selection of all three of these are going to affect the success of your inverse solution. So I'd like to go over some of the optimization methods that are in the literature, kind of going this way around. I'll go over the lookup table very briefly. I think Sylvain, Professor Zhu covered that very nicely. And then this row is what I call direct methods. Simulated annealing. Alexandrakis used keenly two-layer SDA solution and simulated annealing to determine the optical properties, mu A and mu S prime, of both layers and the layer thickness. Hilscher used a genetic algorithm to find the optical properties and actually compared it against a Levenberg-Marquardt and found that the genetic worked for his particular measurements. And then yesterday you worked with the integrating spheres, and Scott Prahl, within his algorithm to determine the optical properties, used a simplex method. And I'll finish up with the Levenberg-Marquardt method, which has the benefit of derivative information helping it find the minima of the chi-squared. And this is just one of many papers that use this method. Avenatti used it in OCT measurements to find the scattering coefficient. So I'll go very quickly through this, but the way the lookup table works is that you have the parameters of interest. In Sylvain's case, he showed mu A and mu S prime pairs, and you create a table where you increment these parameters. And he had two different spatial frequencies, and you determine the reflectance. You create this table that looks like the one here. Different spatial frequency along this axis. Over here, different one. And then you can see the different increments of the optical parameters here. And you do this all before solving any inverse problem. You put all the time and effort into creating this lookup table. And then when you make measurements, you look at the intersection of where it lies in this grid, and you do some sort of interpolation to find out what your optical properties are. So it's nice, easy, works really well, and it's very straightforward. He used Monte Carlo solutions. So as we saw, I think Rolf presented this picture. One of the needed assumptions is the orthogonality of the parameters that you're looking for. This is, I think, Scott Prahl's paper. What you see a collapse here of the intersection of these parameter G varying and the albedo varying here. You can see in this region here, you can have difficulty determining, separating these two parameters and identifying which of them gave rise to the measurements that you've made. So now I'll talk about simulated annealing. This is one of the first direct methods I'll be describing. And the way this works is that you set initial parameters. You take an initial guess of your parameters, your say mu A and mu S prime, or G and N, and you pick your step size based on a current temperature T. And this is where the simulated annealing comes from. You have this temperature cool down schedule, which the temperature is large at the very beginning and then reduces as you move through your algorithm. So you're taking bigger and bigger, you're getting the coarser, you're traversing the coarser regions of the chi-squared map first, and then you fine tune it. So you determine, when you consider a change to this delta A based on the current temperature, you look at the chi-squared value at that A plus delta A, and if you've reduced your chi-squared value, then you accept it. If you've increased your chi-squared value, then you roll the dice and you select a random number to see if it's below this, what they call a metropolis criterion. And if you are, then you accept this delta A and move on. So you're actually accepting movements through chi-squared space in which you've actually increased chi-squared, but it actually moves you out of local minima, which is one of the benefits. And you keep on doing this. As you're going, you're reducing your temperature, and after a certain number of trials, you've achieved your lowest chi-squared. So I'll show this to you conceptually. So here's kind of a schematic of a chi-squared map. You have, say, parameter that you're looking for here, A1, your parameter 2 here. These are iso curves of equal chi-squared value. And I'm trying to depict here through these colors that there's a trough here, a global minima to the chi-squared value. And over here you might have a local minima. And so this simulated annealing will allow you to get yourself out of this local minima and find this global minima. But the cool-down schedule is all user input, and it has to be slow enough and not too fast, not too quick. And so in order to have things like this happen, to come out of this local minima. So those are all user inputs. Could be tricky to tune them to your problem. The next direct method is a genetic algorithm, and Hilscher had good luck with this one when compared to Levenberg-Marquardt. You pick n parents, and these are each parent is a set of optical properties. And then you randomly produce m pairs. So you take these parents, you team them together, and you make m of these teams, and m is greater than the number of parents that you started with. And then you take the average optical properties of each parent pair and a Gaussian distribution about that mean, and you select children. So they call this mutation. So you're taking the properties of each parent, Gaussian distribution, take the average Gaussian distribution, and then you pick your children. And from that, you evaluate your chi-squared value of these children, and you select the ones with the best chi-squared value, and you start another generation. So the idea behind this is kind of survival of the fittest, hopefully through generations. I think Hilscher used 10 generations to achieve the minima to his chi-square and the determination of the optical properties that best fit his measurements. So the con of this method is that numerous function evaluations are needed, and that it doesn't scale with complexity. If the number of parameters that are mutated are large, you can really expand your chi-squared domain fast, and so that can run you into some problems. And the last direct method is, oh sure.
Two slides, please.
Yeah, right here. So for this, so you start with some parents, and each parent has a random selection of properties. So we're talking about, I guess, mu A or mu S or something.
Yeah, for instance.
And then you go through this genetic algorithm for one pass, and then you iterate back up and create another set of parents.
Yeah, from these children.
Are the parents always randomly selected from the space, or do you start to...
No, they're only randomly selected the first time. And then, okay, so the children, of course, go through a Gaussian sampling here, so there's randomness there too. But whatever children are produced here, they become the parents.
Oh, okay.
Yeah. So the simplex method is the method that was used in the integrating sphere, identification of optical properties. And a simplex is a geometric shape. And in the case of this algorithm, it has dimension, or it has the number of vertices of that shape is one more than the parameter that you're looking for. So say you're looking for 2 parameters, it's a triangle. If you're looking for 3 parameters, it's a tetrahedron, and 4, and so on. So let's just kind of keep it to a triangle, because then I can show you pictures of it and show you what's happening. So you set up an initial set of vertices. So let's say you have 3 vertices of a triangle, and each of those vertices are identifying optical properties that your random guess of optical properties. And you evaluate chi-squared at those 3 vertices, and you order your chi-squared in magnitude. And you take away, omit the one with the highest chi-squared, and you look at the rest of the vertices. So let's say it's a triangle, and so one of the vertices is going to have the highest chi-squared. You look at the other 2, which span a line, and you get the center of gravity between those 2 vertices of the chi-squared values. And you reflect. So you find out where that center of gravity is. You flip that triangle. So so you have, say, you start with these vertices, this one, and this one. And this is just a schematic, so I don't know if it's just what I drew so you can see the problem. And you find so this has the highest chi-squared. You look at the centroid here, you just flip that triangle over here, and now you have a vertex over here. And that, you evaluate the chi-squared at that new position, and you find out there's 3 cases. Its value is internal to the ones that you have, it's less than the smallest one, or it's greater than the biggest one. And through these 3 cases, for instance, if it's in between, then let's get rid of the biggest one and merge that guy in. And if it's below, then maybe we should expand a little further, make that triangle go a little further, and see if we can make it a little smaller. And through that, you figure out whether you take the one that you were at or the one that you were expanded and start over. If you are bigger than the largest chi-squared value, then you contract. You pull back, after flipping, you pull back that vertex. And you determine whether the contracted point is better or not, and you go through. So basically, it's this triangle that's kind of flipping and expanding and contracting through chi-squared space. You start with these 3 points, you flip, maybe it's less than the smallest one, so let's see if we can get it even less, more or less. We expand, or maybe it's bigger than the largest one. Let's pull back a little and see if that improves it. Or let's reweight everyone and move them close, move them together simultaneously. So the typical values of this reflection, these are values in which you're determining this alpha, your reflection point, your contraction point, your expansion point, these different factors, alpha, gamma, rho, and sigma here. Typically, you just flip the triangle, and then this is for expansion, you double. This is contraction, and then this is reduction. So this is the method that was used to find that minima in the integrating sphere. And you can see, though, if you pick a too small simplex at the very start, you could be, like this little triangle could be just kind of moving around in one little area of the big chi-squared region. And another pitfall of it is that it can converge to locations in which the derivative of the chi-squared is not 0. In other words, you'd be stuck on the side of this hill where the minima is actually here. But for the inverse adding doubling, it appears to be working very well and is a viable method for that inverse solution.
Question about this?
Yeah.
So the top right, that blob is a local minimum,
Yeah.
not the global minimum.
Uh-huh.
And so if your triangle was too small and close to that local minima, you'd get stuck there?
Yeah, I think so. Although there are, there are chances in which you could, once you reflect, there's these chances where you expand or contract. And I think based on the value of gamma here and rho here, you may move yourself you may expand outside and get yourself out of there.
I see.
Yeah. But those are all, user input. I think the ones I showed you are the typical values. I'm not sure if Scott used those values or not, or he had hybrid method, because this seems to work very well.
I'm just going to add a comment. You're right. In many ways, the Simplex method has, some lack of robustness. It can trap you into a subregion of that chi-squared space. In the context of inverse adding doubling, if you look at Scott Pearl's paper, he actually uses the actual reflectance and transmittance data intelligently to pick proper initial guesses. So if you look at that, so in the Simplex method, the initial guess for the optical properties is if it can be selected intelligently, it will dramatically improve the robustness of this inverse model. Whereas you'll see other methods that Carol will be discussing are less sensitive to these initial guesses.
Oh. Thanks, Wasson. Good add. I didn't realize that. So now I'll go into the gradient-based methods and what the advantage of having the derivative. The simplest is this Newton-Raphson method. You might have seen it in a numerical analysis class, which you're trying to find the roots of some objective function f. And you start with some initial guess, you evaluate the function, you take the derivative, and then that updates your next estimate of the root of this objective function. And this update is found in the following way. And for the general iteration n+1, you take the previous iteration and you take the function evaluation divided by the derivative, the previous iterate. In our case, our objective function to minimize is the gradient of chi-squared. So here's the gradient of chi-squared, and here's what it looks like in an expanded way. See here we have the derivative of the model function with respect to each of the parameters that we're seeking to find. And because the gradient is the objective function, we need to take the derivative of that in order to use this method. So we take the Jacobian of the objective function, and this is the p by p Hessian matrix given here with components shown here. And in matrix form, you can write this as a vector A at iterate n+1 is the previous iterate minus the inverse of this Hessian times the gradient matrix shown on the previous chart. Now, so that was the Newton-Raphson. The Levenberg-Marquardt takes that method and adds a little twist to it. It's a method that combines two methods. I think that gives it its power. It combines the steepest descent used far from the minima and an inverse Hessian near the minima. And I'll show you how that works. If you can rewrite equation 8, this update matrix, in the following way, where you have matrix A, and this 1/2 the Hessian, 1/2 is just in there because you have a derivative that brought down a 2. And you have your parameters, delta parameters that you're looking for, and your gradient value over here, 1/2 gradient. So you have an AX equal B here that you're solving for delta A. And what Levenberg-Marquardt does is that on the diagonal of that matrix, it adds this 1 plus lambda, lambda being greater than 0. And as that lambda gets changed during the algorithm and magnifies that diagonal of the matrix A, which is the the Hessian. So in kind of written out in full glory, you have this matrix here with 1 plus lambda along the diagonal. You have your unknown, and here's your right-hand side, your B, your gradient. So the way this works is that you pick an initial guess. And this is a value I've used in the past, but you could start with a smaller lambda. You start with this value. You determine what your delta A is, given this lambda value. You evaluate what the chi-squared is at that delta A. And if you've created a smaller chi-squared than the one you started with, well, this actually says this: if this is the new one is greater than the one that you started with, then you multiply your lambda by a factor of 10 and you repeat. So basically, you're amping up the diagonal, and this is making the problem a lot more invertible. The Hessian is becoming a lot more invertible, and if you have found this delta A, you found a better chi-square, then you go with that delta A and you repeat. You update your lambda. And convergence is attained when the change to chi-squared is negligible, or where the difference between two iterates is below some predefined epsilon. So one of the negatives that happens with this Levenberg-Marquardt is that you do find yourself sitting in local minima sometimes. But one of the ways that we have mitigated that problem is that we have chosen several initial guesses and ran the inverse solution and found where the majority of them converged. So I'm going to shift gears now. Is there any questions to what I've shown yet?
Thanks. Are there any time references, like to know how much time each method takes?
It depends on the number of function evaluations that, and each method varies as far as that is concerned. Of course, in the gradient-based methods, you have to allow for time for the derivative calculation. But on, for instance, the genetic algorithm, depending on how you mutate, you may have lots of function valuations there too. So yeah, a lot of the time spent is based on the parameters that you pick and how fully you kind of scan the chi-squared region because of the algorithm that you're using. The gain in gradient is that you're following a single path as opposed to kind of exploding all over the chi-squared map and evaluating on a variety. The other methods, are not somewhat blind, but they're kind of canvassing the whole region. Whereas the gradient method, although you have the addition of the derivative, you're moving along in a directed path. So, yeah. Uh-oh.
Just a very quick question. Did people try to combine these different approaches together? Like, it seems to me the genetic algorithm would be a fantastic way to pick your initial guesses for other methods, for instance.
I see. I do not know about that, but that sounds like it's a good possibility. Kind of reduce the problem to a smaller scale, and then pump up something that works for that scale.
So my question is, when do you stop? What is the criteria that you predefine? How do you know that your solution is good or not?
Usually you stop when you're not improving anything. When the value of your chi-squared is not changing, you bottomed out, you're moving around and you're trying, and there's many iterations in which you're not changing that, then usually there's a stopping criteria, or the fact that the vector difference between two successive parameters that you're finding is below some sort of epsilon. You're just like making really little, you're down in this, you're down in the global minima, but you're just like, making really, really little fine-tuned steps. So those are the two general reasons why you would stop the iteration.
So for scene one, maybe I have a experiment in genetic algorithm, very tricky. You take a long time and you have a different, a solution at the end. So it's kind of tricky. Yeah. So for genetic algorithm, it's very random. It's very random. At the end, you maybe end up with different solution, and you're stuck with that. So, but maybe I see a good reason to use that as the initial guess. Yeah, as you
Yeah, you have to remember that the chi-square space is a very complex space, and we're searching it in a kind of a nonlinear fashion, so it's very easy to get stuck. It's also very easy to converge to a local minimum, as we've seen, and a lot of the methods work their way out of those little troughs and try to migrate towards the deepest one. With genetic algorithm, there's a learning that is stochastic, of course, as you point out, but it is not a guarantee of convergence to the appropriate answer either. And in fact, I know of no search method in such a space in which you can guarantee convergence to the absolute minimum.
So just one thing I want to emphasize is that no matter how good your algorithm to do the inverse problem, if the intrinsic topology of your chi-squared map is poor, that is, you have picked measurements that do not provide independent sensitivity to the parameters you're trying to recover, you're always going to get a poor inversion. So, just to map this to the lookup table, this is a depiction of a hypothetical chi-squared map. You see that it's oriented at an angle relative to the two parameters, which means that maybe it's not perhaps the best two measurements that you made. You want to think about the measurements you make in terms of the chi-squared map, and you can do this if you have forward models that can predict what would the chi-squared map look like for the two measurements or multiple measurements you're looking at as a function of optical properties. And then you can play these games with your forward solver to figure out where would be the best place to put my measurements to get a chi-squared map that has hopefully a single minimum, a minimum that is very confined, and has good orthogonality between the parameters that you're looking for. So this is actually where forward solvers can help inform where you make your measurements to make the inverse problem easier to solve.
Thanks, good questions. So I want to, before I describe perturbation and differential Monte Carlo, kind of remind you that why you might use a Monte Carlo solution. You can use them for measurements very close to the source. They're valid for any optical properties. You don't need mu s prime to be greater than mu a. And they can be used for any type of tissue, very heterogeneous tissue definitions. So perturbation Monte Carlo, Jerry talked about this on Monday a bit. It allows you to provide any number of forward predictions, and these are RTE predictions, so they're transport rigorous predictions, derived from a database of photon biographies based on a baseline tissue property. So say you're trying to find cancerous tissue transformations, but you know what normal tissue optical properties are, and you run a database based on those normal optical properties. And the way that you would you get this model prediction, say, be it reflectance or fluence, based on these baseline optical properties, and they're determined by a random variable C, determined by a measure based on those optical properties. And this measure is let's say, probability density functions that describe the random walk process as you move the photon through the tissue. And so you evaluate the model function based on these parameters in using this random variable in that way. Now say you're interested in a what if. What if my optical properties were these? Then one way you could do it is you could determine the model prediction of that by running another simulation. You could run a simulation with these changed optical properties. But instead of doing that, you can adjust the weight, apply a weight factor to this random variable in an appropriate way such that your result is still an estimate of your model prediction with that change, but you can use the random walks that were generated off the baseline optical properties. So this weight factor is the perturbed to unperturbed measure, and you apply that to your random variable. So the benefit is that you can store the pertinent information of these random walks into a database and then reread that database in a very quick way, much faster than regenerating the random walks, and determine a multitude of delta A changes and what your model forward prediction would be. But in addition, there's a double benefit, is that there's correlation now. Now you're using the same set of random walks, you're applying the weight factor, and so you're getting correlation, and this correlation actually identifies the effect of that perturbation in a stronger way with less uncertainty than if you were to have run an independent simulation. So there's a double benefit there. And this perturbed estimator can be differentiated to provide differential information that you can feed into a gradient-based algorithm. Another thing I want to point out is that you could segment the tissue, have optical properties varying in all segments, and apply this weight factor as the photon goes through its random walk. You see where it traverses, and each time it goes into a region that has different, the delta A incorporates changes to those optical properties in that region, you can apply the weight factor. So you can see the changes within a heterogeneous model tissue for a variety of different changes to optical properties. So the disadvantage is that it's a perturbative method. So it's best when the perturbations are small. You can imagine that if the delta A is very large, that weight factor that I'm applying can get unwieldy. Now it can be shown that the mean would produce the same mean, but the variance can get unwieldy. And that's the drawback of this method. We use this method to look at the optical properties of cervical tissue, layered cervical tissue, and just to give you an idea, we found good success in identifying mu-A when you perturb it from about 0.33 to 3 times the baseline mu-A, and changing mu-S from about 0.7 to 1.3. There's a software in the MATLAB interop download that I put in to put a little example if you wanted to try it. It runs a little database and then it applies the weight factors and solves an inverse problem. So this is just a little schematic of the flow of that solution. You run your baseline random walks, you store them in a database, you determine your model prediction. At first this delta A is 0. You determine your chi-squared, taking your measured, and you determine if it's converged. If not, you use the differential Monte Carlo to determine your update to this delta A, and then you cycle through until 2 iterates are less than a predefined epsilon, or you've made a minimal change to your chi-squared value. have any questions? So now I'll go on to optical tomography. And to kind of motivate what's going on here, I thought I'd throw up a picture of actual system. This is Brian Pogue's lab, and they have a volume of tissue here. They have 16 sources and 16 detectors surrounding it. I think it's every other one. Here's the actual system. So the tissue sits in here. And here are some results they have for determining optical absorption and reduced scattering of tissue. So the way these equations work is now that the unknowns that you're looking for, that vector A, is now a 3D map of parameters. So you segment the tissue, and the optical properties in those segmented regions are what you're looking for now. And now we've added into this chi-squared a sum over all sources. So he had, in his particular example, 16 sources, 16 detectors, total of 256 measurements at the tissue surface. However, you can imagine he segmented the tissue in way more segments than 256. So you've got P, the number of parameters that you're looking for, far greater than the number of measurements. And so you have an undetermined system. This is an ill-posed system, and a lot of times regularization methods are applied. And in fact, Brian Pogue's lab does apply those regularization methods. So if you rewrite this in matrix form, you get a chi-squared that looks like this. You get the measurements minus the model transposed multiplied by this. And to minimize it, you set the derivative with respect to the parameters equal to 0. So the left-hand side of the previous equation becomes 0. You get this on the right-hand side, and J is the Jacobian, which is the derivative of the model at all the detectors. So now you have this dimension of S times M times P, the number of parameters. And you can solve for this delta A in the following way. But like I said, a lot of times they use this Tikhonov regularization, the addition of this factor here. And this regularization factor could be scalar, but in Brian Pogue's inversion, they actually found it to be a function of the tissue segment. So this lambda along the diagonal is varying. And you find this delta A through iterative methods like Levenberg-Marquardt, or direct methods are sometimes used too. So now I thought I'd go through some examples of actual inversions. And I wanted to explore this chi-squared, not in my schematic, but in actual, using some actual data, and look at the effect of that topology based on the number of measurements, the amount of noise in your measurements, your initial guess, the type of measurements that you use, and the location of the measurements. And I did this all within using MATLAB, and there's a Levenberg-Marquardt LSQ curve fit routine that I used in these results. So first, I considered the spatial domain of spatially resolved reflectance. And here we're looking to determine optical properties. So I took 6 source detector separations in this span for my measured data. And I created the measured data using something we call NURBS. And I have a feeling that I'm the first one talking about NURBS. Okay, so NURBS, I'll take a little aside here. NURBS, you'll see it in the GUI on the pull down. There's of this solvers. There's a couple of SDAs at the top, and then there's one called Basic Scaled Monte Carlo. And I'll start with that. Basic Scaled Monte Carlo is a method that Keenly designed in which you run a Monte Carlo for a selection of row and time bins. And through an appropriate scaling of the data, you can determine the reflectance due to changes to mu A and mu S by appropriately scaling that data. And we implemented that, but found that at high times, large times, and large rho, that broke down a little bit. So we came up with a NURBS, which is non-uniform rational B-splines. We actually varied the row and time bin and made them larger as you go farther out so that the variance in them was smaller. So there was this adjustable bin size as well as this B-spline approximation that was going on top of the scaling. So that allowed for even more accurate solution using Monte Carlo for reflectance solutions. So whenever we're using the GUI, that's my go-to as far as the closest to the best solution to the radiative transport equation. And so we're using that to generate our measured data. For right now, we won't add any noise. We're going to use the SDA with a point source as our model function. We'd like to fit mu A and mu S prime. And I set the measured data for mu A and mu S prime to 0.01 and 1. These are the parameters we're hoping to find with our method. And we can see that the ratio here is 100, mu S prime. So we're in the diffuse regime as far as these optical properties are concerned. And then we use Levenberg-Marquardt. So here's a plot of the initial guess, which is set at mu A equals 0.05 and mu S prime equal to 1.2. Here's what the actual value that we're searching for, the measure. Those are the blue. Our initial guess is the red. Here are our row values. Here's reflectance. And our converged values is this green line, and you can see how it moved through. So it started at this value, and this is how it moved through chi-squared space, and it found its minima here. But note a couple things. It's really bad. I mean, the scattering is okay, decent, but absorption is terrible. And another thing to note is that the measured data, it's kind of hard to see, but that the measured value in this chi-squared map is actually sitting over here. It's not actually sitting in this basin here. And like Watson says, there's this oval shape of this chi-squared topology. And so, you know, how you're going to enter the minima, although this isn't the minima, but if you, as you're moving around in the topology, how you move through it is going to vary based on your initial guesses. So does anyone possibly have an idea of what might have gone wrong here? I'll show you the data. And notice that US is decent, but it's mu A that is not doing good. So, and remember that as Sylvan said, mu A needs path length. You need a certain path length in order to get mu A. So, any volunteers for ideas of what might have been wrong with my setup here?
So it's detectors of radial flow?
Yes. So, I moved them, let's move them out. Let's see how we do. So I moved them out to 6, same number, but out to 1 to 6 millimeters. And now you can see how the converged values are a lot better for mu A. We started here, we entered, this is actually another trough. This is the same initial guess, we went to a trough over here to the right. Over here. So this is the actual global minimum, the minimum we want to find, and it found it fairly well. And now you can see how the measured is also sitting in this trough.
I have a question, Carol.
Oh, sure.
So, in these two problems, it seems as though actually the inversion algorithm did its job. It found the global minimum, but somehow that global minimum was not, did not pertain to the actual values. And in fact, plotting the location of the true optical properties was actually at a location in the chi-squared space that did not correspond to a minimum at all. Can you resolve that kind of contradiction or quandary?
It's because of the placement of the measurements, and because this map is the result. It's the chi-squared value of the difference between the measurements and the model prediction at a given set of parameters, but that those measurements originally, so let's go back to that one, this one, the measurements were at these source detector separations, right?
Can you go back to the previous slide?
You mean the one that we did
The
next?
setup, the
Yeah.
setup. No,
Oh,
all the way
setup.
back. So noise was not applied to this data?
No noise, no noise. It's because of the model and the choice of the measurement domain. Yeah, that caused.
So the model isn't exact. So it could be that
Yeah.
if the model were exact and your measurements were exact,
Yeah.
you could potentially still recover the optical properties, but perhaps with not very good accuracy, because if you place your measurements at source detector separations that did not have sensitivity. So it's really a combination, it would seem, of not using the proper model,
Yes.
as well as putting your
Yes,
measurements in a
it's
bad
combination
location.
of- Right. So I showed, let's see. Yeah, so now let's add some noise, 5% noise. And with this addition of noise, the convergence of UA is slightly degraded. This is a lot of noise, but just to give you a feel that when you add noise to the measurements, it can affect how you recover your optical properties. Makes sense. Reasonable result. But let's say we chose the same amount of noise, but a different initial guess, and we get some improved recovery because you may come into this basin in a different way using the gradient information. So my second example is to look at spatial frequency reflectance, also with wavelength. And so I've chosen these spatial frequencies. I chose 8 wavelengths in this realm, and I simulated my measured with NURBS with 2% noise, and I used that as my model function. This is called the inverse crime. Shouldn't be using the model that you created your measurements from because you're kind of using like with like, kind of cheating there. But we're just going to do it for the sake of illustration on this example. And say we want to fit these parameters, oxy and deoxy hemoglobin, and A and B of the scattering power law. So say those are the parameters that we're looking for. For our measured, I took the skin parameters to generate my simulated measured data, and I used these are the skin power law parameters. And in this case, we have, just kind of a step back. Well, now we're looking for chromophore concentrations and these AB parameters. And those get converted to mu A and mu S across wavelength, as we saw in the spectral panel. And that kind of conversion enters the model function. So we're going to be solving for these parameters directly. The model function now takes those mu A and mu S spectra and uses NURBS to create our forward predictions as a function of spatial frequency and wavelength. And this can be done, of course, I just happen to choose these chromophores, any other measurements. So I took an initial guess. So here are the measured, and this is just for the HB and HbO₂. Here's the measured. Here's my initial guess, the first 2 parameters of HB and HbO₂. And this shows that my recovery isn't very good here. It's terrible, actually, for these. I'm trying to see where it starts here, and can't see where it ends up. But anyways, oh yeah, it's kind of hard to see on the screen. It ends up down here. So it starts here, and here's how it's moving through chi-squared method. And here's where the measure actually sits. So that's HbO and HbO2. Here's the coefficients, A and B, of the scattering power law. And these do pretty good. This is actually coming in and finding the trough of this chi-squared pretty well. So again, what do you think possibly that has gone awry here? It's very, very, bring this up again. Kind of in a similar vein as before, we need that, those chromophores need that path length information. And so, anybody, Summer, probably, it's in the selection of these spatial frequencies. And if we change our spatial frequency to 0 and 2, now we see that we get improved recovery of these chromophore, Hb and HbO2. And the power law is decent still. So I just did the same thing with a different initial guess just to see how robust finding these minima is, and actually it goes to exactly the same value. Yeah. Oh.
Just curious, so what was the change in spatial frequencies that in the previous one and this
The
one?
first one was 0.2 and 0.3.
Okay.
Yeah, and in the second one, it was 0 and 0.2.
So how does that affect the results? They seem to be in the similar scale, but then one is 0 and 0.2, and you have delta 0.1 and 0.3. So could
Yeah.
you explain a little more how that affects?
Yeah, so in spatial frequency domain, the larger the number, the more frequent the distance in between the sinusoidal wave. And so you're actually spanning smaller bananas, if you will, of the tissue. The path lengths are shorter for the higher spatial frequency domain numbers. Oh, Sylvan, maybe you. And then for when you reduce it, you're actually probing deeper into the tissue. There's longer path lengths. The sinusoidal pattern is stretched out farther apart. Using 0 is key, I think, to inverting the solution. In fact, if you look at the table lookup, one of the axes is 0. And I think the other axis was 0.2. Yeah, so 0 I think is key. Helpful having someone in the back of the room. So, that concludes my talks. I just wanted to summarize by saying that, minimization of this chi-squared is key to finding solutions to your inverse problem. They can give you fits in more way than one. It'll fit your measured data, but it'll pull your hair out sometimes too. And that your aim is to pick a measurement, a type of measurement that is sensitive to the parameters that you're trying to seek. Pick a model that is appropriate for the measurement type. I've exposed you to the fact that maybe a Monte Carlo solution might provide you a solution when you have these complex tissue types, and they can be done in an iterative scheme in a fairly fast way. The choice of your optimization method will definitely affect your ability to resolve these optical properties. And I also wanted to mention that all the examples that I showed, the 2 examples I showed at the end, I I took the MATLAB interop code and I just expanded it. I just put in the particulars. And so you two can play around with that if you were so inclined. I kind of have a question for everybody. How many people have run inverse problems or optimization problems for some reason or another? Maybe not maybe in biomedical optics, but maybe just an exercise in school or even in work? Does any? Oh, okay. Did you guys use Levenberg-Marquardt? What did you use? Matt, what did you use?
Newton-Raphson.
You used
It was
Newton-Raphson?
numerical methods, but right around. But we didn't actually use it to look at anything interesting, unfortunately.
Yeah. It's nice to know that something you learned is actually being used.
So Carol, I have a question. So, what is the process by which you go about determining what algorithm might be best? It would seem that different algorithms are used for different problems, and that choice seems to be problem specific. So the question is there anything one can do a priori to at least select an initial algorithm that may be a good, pardon the pun, a good fit for your problem?
Right. Well, you know, generally speaking, I have to say Levenberg-Marquardt or a gradient-based method is probably the predominant way to go. Most of the people start with that. But, you know, Hilscher had good success with this genetic. He had an unusual situation in which he had this rectangle of volume and a source, two sources at the top of this rectangle, and then he had detectors along two sides of it. And I think the reason why his genetic did so well is there was this trough here. There wasn't like a bowl, there was a trough. And he actually shows how Levenberg-Marquardt goes into that trough, but it doesn't know how to go along the ridge of that trough. And so that's why genetic got him there. But one way, I think you and I have discussed maybe, you know, you could create a chi-squared map and give a look at what the topology looks like. And if it is something in which you have some sort of trough here or something where, you know, your gradient, if you get stuck in this trough, this gradient isn't going to get you moving you anywhere, then the Levenberg isn't going to help you there.
So maybe I can follow up, and it's nice that you have your overview slide where you summarize all of the techniques you discuss. Is that, could you map or say for each method what sort of chi-square topology may be in the quote-unquote power stroke of that method? You know, because I think it's quite clear, just as you said, in genetic algorithm, this seemed to work well, and it's also, you explained why Levenberg-Marquardt doesn't work so well. So could you maybe talk a little bit about simulating annealing and simplex and what chi-squared characteristics may feed well into the characteristics of those methods?
Well, the simulated annealing, as you know, I described this, you know, gets you out a local minimum. And so, you know, of course, if you have this topology in which it's undulating with a lot of these minima in regions in which you might choose initial guesses and that you're going to get stuck, that would be the selection. If you have one big bowl with a sharp gradient, then, you know, Levenberg-Marquardt's going to get you there, because you don't want to necessarily percolate up in chi-squared map to allow you to find the minimum, the local minima. So yeah, so it depends on that topology. The simplex, yeah, it's, you know, I'm not sure exactly what topology its benefit would, how it would benefit its application. Like I said, in the drawbacks, it can get stuck on a slope. Yeah, I don't have an answer for that.
Carol, I'm just totally speculating, might simplex be faster?
Oh, yes,
Levenberg-Marquardt if your initial guess is close to your converge.
For sure, just like you answered the question about Scott Prahl and how he took aims to get that initial class close. Yes, it's very fast, it's very fast. So yeah, but in terms of the topology of the chi-squared, I'm not sure what that needs to look like for it to work fast.
So thank you for the great talk. So right now I just say that the method is really powerful, very useful, but it's very complicated to you.
Which one?
I mean, everything. Okay? For example, you need to select a method that master your problem,
Yes.
that you don't know to begin with. You need to have a perfect measurement that allow you to track back what is the optical property, and then you have to have a very good initial guess that you don't know.
That you
So
don't know.
everything is fuzzy,
Yeah.
and you need to have an exact solution.
Yeah,
So
it's a hard problem.
yeah.
Yeah,
So,
but you can constrain things, like for instance, you know your optical properties will not go negative, or shouldn't go negative.
Okay.
And you can constrain them, although I actually have seen the optical properties go negative and come back in a Levenberg-Marquardt algorithm, and come back in and converge to the right values. So constraining can sometimes be good, but it can run you into problems because it doesn't allow the algorithm to do its thing. You know, it doesn't know that you shouldn't go there. It's just trying to find the minima in the chi-square.
So my assumption right here is in order to use those methods, you need to be very experienced
Yeah.
user to begin with.
Oh, to use the method? Actually, MATLAB makes it very easy for you to not really know too much about. You just set the parameters and you can use, is that what you're asking? And it will use finite differences if you can't provide the derivative information. It will use finite differences to approximate the derivative for you. So you just need to give it a little script file that gives you the forward solution for your particular parameters, and an initial guess, and it will do its thing for you and give you the recovered values.
So let me just add, so these techniques are pretty much all fairly standard, and if you're experienced with MATLAB, there are already algorithms out there for any one of these techniques. I do want to clarify that, these techniques are fairly robust as long as your measurements are sensitive to the intrinsic parameters that you want to recover. And so they are, they can work in realistic measurements with measurement noise, even when you're using a model, such as an approximate model, such as a standard diffusion approximation, as opposed to Monte Carlo, if, in general, SDA is a reasonable regime to operate in. So I don't think the situation is as dire as you thought, that you need a perfect model with perfect measurements, with an extremely robust simulation method. So, I mean, after all, these methods have been used in biomedical optics for 20 years, even using simplified models with very good outcomes. So let me get others in the discussion.
My question's really towards the application of this, and there's a lot of work being done with layered tissues, like my work in the retina, but other people who work with are doing like cancer studies, where we're really looking for a way to go find and measure changes in the tissue properties before we see clinical, malformations like cancer or like diabetic retinopathy. So that's really of interest of non-invasive ways. So we really want to be able to measure the optical properties. So between the measurements and the models, what kind of match would we really need there?
Well, there's, Alexandrakis right here used a 2-layer. I don't know how many layers is in your application, but there's a standard diffusion solution to a layered tissue. It relies on the fact that that top layer is thicker than L star. And of course you have, I don't know, in the eye, maybe that sounds like possibly small source detector separation and minimal absorption. Yeah, there are, and of course an analytic solution is going to be able to be calculated very fast. You also have the availability of Monte Carlo solutions too. through the use of the perturbation Monte Carlo that I described. You could perturb, and that's what we did in a two-layer system. We perturbed the optical properties in the top and bottom layer. We're able to determine those given a set of measurements. And those would need no restrictions as far as optical properties, source detector separation, or what have you in your particular application. So those are the two that come to mind. Also, you could have multiple layers there. There is a multi-layer diffusion solution as well. That's available too.
Yeah.
Is that what you're asking?
Well, yeah, I mean, part of the biggest issue is that even though there's a nice optical window into the eye through the lens itself, that we're looking at a scale where a lot of the layers in the eye, there's like 9 major layers of interest, and they're about 6 microns thick each. And it's the small changes in the optical properties are starting to result in vision loss. And it's before we get the gross morphological changes.
I see. So yeah, perturbation, Monte Carlo, and differential possibly would work pretty there because of the dimensions.
All right, thank you.
So is there any generalizability in the shape of the chi-squared maps? So you're doing like a reflectance measurement, and you have some measured thing, so some measured properties. If you have a lot of Monte Carlo models, are the maps going to look the same for similar models?
So you're kind of getting at, like, if you had a perfect situation and you had certain measurement domain, like reflectance versus rho, would the chi-squared map look a certain way?
Yeah.
I don't know if you could generalize that. I have not done any research on that. There's the of course, noise is going to throw everything out the door and skew any kind of assumptions that you might have as far as the general shape. Yeah, I don't know about